Joe, what's so funny? Did you make another joke? No, no, I do not. I do not want to hear another joke. No, I do not. No, not at all. Okay. Okay. For the sake of argument, for people who are going to be filtering in, I'm going to get started in just a moment. I'm just changing some settings on what I have here. Oh yeah, I got your message about the computer being almost set on fire. That was nuts. That is nuts. Man. But regardless. Ooh, I never want to think about that. One of my buddies actually we paid him to build the computer that I'm currently using right now. And we've had this computer running full speed for 7 or 8 years. And we've never had a problem with it. It's fantastic. I don't know. No, it's really cool. It's with like sorry, just check my email too. He designed it with like a dual something or other. I don't even know the details behind it. He's incredibly smart in what he does. But there's a hard drive that is like 500 gigabytes. That's like solid state, and we store whatever we need into that. And then there's the regular computer, which we have like our programs and whatnot on, of course, you know. But anywho's I'll get started. So, Algebra 2, Chapter 11. If you are looking in your textbook, Chapter 11 introduces some of the basic ideas behind statistics. And what's great about every single Algebra 2 teacher that we have at Barnegat, every single Algebra 2 teacher at Barnegat has a background in statistics. It's really great. But, you know, here we go. So let me introduce to you a scenario. Let's just say, scenario. Scenario. Bullet point. You own a grocery store. And want to know customer opinions on something. I'm going to keep it very broad. Or, let's say you run the Department of Education and want to compare high school physics scores to college physics scores. Or you're a researcher. You're a researcher wanting to know if eating fruit reduces the risk of heart disease. Or you run a TV channel and need to know what type of show people want to watch. These are all different scenarios in which a study would be in order. I don't know why I wrote designing a lesson up here. That's really weird. My mind must have been elsewhere, but it really should be designing a study. I apologize for that. But yeah, you run a grocery store and you want to know what customers' opinions are on something. You run the Department of Education, you want to compare high school physics scores to college physics scores. Maybe you want to see how to improve the high school physics scores. You're a researcher. You want to know if eating fruit reduces the risk of heart disease, something that can be very helpful for the average person. You run a TV channel and want to know what type of show people want to watch because you're looking into making money. Each of these scenarios, there's something that we want to find out. And we want to find it out from a certain population. For example, the grocery store owner, their population are people who go to that particular grocery store. The Department of Education, their population would be physics students in high school and college. The researcher, just, I guess, everybody. You want to reduce the risk of heart disease. TV channel, people who watch TV, or maybe a certain age demographic that you're aiming for. I don't know. It all depends. But you want to find out something from a certain population. Now, let's go into a little bit more detail about that, the idea of a population. In each case, you're hoping to find out some characteristic from a population. Population is an entire group of people. Now, who those people are and what those people do, it depends on the scenario. If your population, for example, the grocery store owner was just interested in people who go to their store. The population are customers of that store. The person who runs the Department of Education, their population is just high school students who take physics and college students who take physics. The researcher with heart disease, the population could be every person on the planet. Who knows? A population is just the entire group of people. So if you want to know some kind of characteristic about the entire group of people, that characteristic is called a parameter. These are just some definitions that I need you guys to recognize. That characteristic is called a parameter. We typically refer to it as a population parameter. That's what we call it. Now, we run into a little bit of an issue. It's next to impossible to get a complete picture of a population. This marker is dying on me. I'm going to get a different marker. It is next to impossible to get a complete picture of a population. I don't see how that's even feasible. Every 10 years, sorry, just reading Joe's comment. Every 10 years there is a census done in the United States in which they try to get certain pieces of information about the entire United States. And a census is very costly, and it doesn't get every single person, every single citizen. It doesn't, unfortunately. It's next to impossible to get a complete picture of a population, also known as a census, due to time, money constraints, whatever. One example I could potentially talk to you guys about, think about polling for politics. You want to get the president's job approval polling. If you go to get the opinion of every single person in the United States, by the time you actually get their opinion and gather their opinion properly, mind you, however much time would have gone by, opinions may have changed, and you've spent all this money on unusable information, you know? Or, better yet, imagine a lake full of fish. Imagine a lake full of fish. So here is some kind of a lake. There's some waves, some pretty little waves in there, and there's some fish. There's a fish there, and there's a fish there. You can see them at the surface. There's the fish there. Now, there's a ton of fish in this lake. You don't know how many fish are in this lake. You have absolutely no idea. But the population would be every single fish within this lake. Now, you want to know the average weight of all fish. You logically would be like, oh, catch all the fish, weigh them individually, and then boom, you got the average. If you add them all up, divide by however many there are. But you don't know how many fish are in this lake. And you're not even guaranteed that you're going to catch all the fish in this lake. You could drain the lake, but again, that's not going to be helpful. So instead of a census, you catch a sample. You catch a sample, and we can get a statistic, sometimes referred to as a sample statistic. Now, to be very clear, that sample statistic, that sample average, or however many you get, maybe you catch like 50 fish. I don't know. And then you take an average of them. Really, there's like 10,000 fish in that lake. I don't know how big the lake is. But that sample statistic may not match the population parameter, but that is okay. Because that sample statistic can still tell us something about the population of fish in that lake. It is not feasible to catch every single fish in that lake. So instead, we catch a smaller sample, and now we can do something with it. I tell my AP students all the time the following statement. Quote, statistics is making confident statements with limited information. Statistics is making confident statements with limited information. So you may not be able to catch every single fish in that lake. You may not be able to survey every single person in the United States, but you can get a small sample. That's your limited information. Now, how confident of a statement you make, that depends on a lot of different things. In fact, I can write how confident you are depends on a number of factors. And most importantly, is reducing bias. How confident you are depends on a number of factors, most importantly, reducing something called bias, which is what we're going to be partially focusing on today. Bias is an error that results in misrepresenting the population. Let me give you an example. One example would be getting, let's say, Barnegat High School students' opinion on a certain thing. Let's say you're interested in knowing Barnegat students' opinion on a certain musical group, whoever that musical group is. So you go about and you ask the people that you sit with at lunch their opinion on this particular musical group, and then you get either a yes, I like them, or a no, I didn't, or whatever it is that you got. Your sample is automatically biased. If you're only asking the people that you sit with at lunch, well, reason dictates that the people that you would spend time with have similar tastes that you do. So if you have a certain opinion of this particular group, then your friends might have a similar opinion to this particular musical group. As a result, whatever results you get from that does not represent the population of Barnegat High School students. See, even Joe says people he sits with hate everything. But that doesn't represent the opinion of the population. That just represents the opinion of the people you choose to sit with. That's biased. To go a little bit deeper into this, well, actually, you know what? I'll do that example first. Yeah. Think of soup. Imagine making soup. It's a nice example. I like it. Imagine making soup. You put in the vegetables, broth, and spices. It cooks. Let's just say, I don't know. And then you take a sample to taste. So what people do, they make soup and they take a spoonful, the sample to taste, call it a spoonful, whatever the heck you want to call it. And it's terrible. Why? You're making soup. You put in everything. The vegetables were fine. The broth was fine. The spices were fine. You followed the recipe. It cooks. You take a sample, a spoonful, you taste it, and it's terrible. Why? Why? You never mixed the ingredients. You never mixed the ingredients. The general idea behind taking a sample is you have to make sure that you are randomizing who is in your sample. I go back to the musical group. If you only survey the people that are around you, logic dictates that they would have a similar opinion to you. That's not a random sample. If you do not mix up that soup before you take a sample, you have not randomized, and you have completely biased the results. The population of that soup is not represented in your spoonful because you never mixed it in the first place. Once you mix it, once you randomize that soup, then you can say, oh, yes, this spoonful does represent the entire soup if it's mixed properly. It's a key piece of information that we do have to recognize. Randomization is absolutely needed. Randomization is absolutely needed. In fact, let me write down this statement. One way to reduce bias is to take a random sample. By the way, random, just as a side note, random is when we know the possible outcomes, but not what form. I don't want to use the word form, but not what outcome will result. That's how I want to write it. That's the general idea behind randomness. You know the possible outcomes, but not what outcome will actually result. You could take a die, you roll that die. Well, you know the possible outcomes are going to be 1 through 6, but you don't exactly know which one will come up. Is the general idea. Okay. Couple of side notes here. In terms of notation that I'm going to be using. Population parameter versus sample statistic. If you're talking about population parameter and an average, like let's say you take the average height of every single person at Barnegat High School, or the United States or whatever, or you take the average GPA of every single person at Barnegat High School, let's say that's your population parameter. We typically use this symbol. The average symbol is referred to as mu. It is the Greek letter mu, or the 151st Pokemon. If you are taking a sample, like let's say you only took a random sample of 100 students, or what have you, and then found their average, we refer to that as X bar. So I'm just going to be using these notations in the future, moving forward. If I'm referring to mu or X bar, depending on which one, I might be talking about the population, I may be talking about the sample. There is also one thing we will be talking about in reference to standard deviation. Standard deviation is a very common statistical notation. It is in reference, for the lack of a better term, it's in reference to like average deviation from the mean. Like you could deviate above the mean or you could deviate below the mean. But if you look at the positive distance from the mean, the absolute value from the mean, and somewhat took an average, it's not exactly how it's done, but somewhat took an average, that would be standard deviation. Now, for population parameter, we use the symbol known as sigma. It is another Greek letter. It is lowercase sigma. There is a capital sigma, but this is lowercase sigma. For the sample statistic, we use the very original S. I know. It's quite remarkable. It's just the letter S. Now, we could also be dealing with proportions, which we will deal with in the future. The population parameter for proportions is this letter. It is commonly referred to as the letter P. I know. Very original. But if you're talking about a sample statistic, we use this. P with a little triangle on top. That's not even a triangle. It's like a little arrow on top. And we refer to this as P hat. Yes. Fat, I guess. Whatever. But it's P hat. Just for the sake of argument, I'm going to be using these moving forward. Let's talk about the 3 different ways that we could gather information. There are 3 main ways to collect samples. There are three main ways to collect samples. One, we could do a survey. Yeah, boom. A survey is just data collected from responses given by members of a population. Now keep in mind, in a survey, they are freely given by members of a population. So keep that in mind, because there's a huge difference between a response that's just given by a person and information gotten a different way. Let's talk about experiments. You can collect data from an experiment. Basically, now, experiments are much more complicated than what I'm going to do or what I'm going to write, but I'm writing a simplified version of that. The sample is divided into two groups. Experimental, who undergo a treatment, some kind of manipulation, and a control group who don't undergo treatment. Now, keep in mind that for the control group, sometimes helpful if control group or control don't know about non-treatment. If they understand that they're not actually going through the treatment, or if they don't know that, it's like it's information that's kept from them. These are referred to as like blind treatments, or in some cases, and you've probably heard this word before, a placebo. So if they're unaware of the fact that they're going through an experiment, and this could be for the experimental group as well, it could be referred to as a blind treatment, or if the control group is given a fake treatment is referred to as a placebo. People have probably heard of the phrase placebo effect, or something to that, something in regards to that. And that, yes, that's involved with this. The placebo effect is not something we're going to get into, but it's basically where the control group is given a placebo and they have a very similar change, or similar compared to the treatment group or the experimental group. But I'm not going to get into those details because that's not a part of this lesson. 3 main ways in which we can collect samples. Number 1, through surveys. Number 2, through experiments. Number 3, through observational studies. Observational studies, basically, members of a sample are measured / observed without being affected. So for example, again, let's say you're trying to figure something out about the waiting habits of people at a stoplight. I don't know. And you stand on a corner and you're assuming, well, they're randomly going to show up to that stoplight, and then they show up, and then you observe and record or measure whatever you need to measure, and then they go on with their day. They're not being affected by you, and you're just simply gathering that data in a controlled environment. Well, not really a controlled environment, but as close as you can get to a controlled environment. That would be an observational study. Or You go into the records of Barnegat High School and you look at average GPA of, I don't know, the valedictorian for each of the past 15 some odd years. That would be an observational study. You're measuring a certain value about that person without affecting that person. That would be an observational study. Now, I want to talk very briefly about cigarettes. There is a common misconception about correlation, which correlation is not the focus of this lesson, but I just want to do a little aside right here. First of all, correlation does not equal causation. Example: smoking causes cancer. We cannot prove this by simply showing the correlation between the number of people who smoked versus number of people, let's go specifically with lung cancer, with lung cancer. Unfortunately, you can't do it. You can't prove it that way, just because there's a correlation. In fact, if you go back to the 1960s, a lot of cigarette companies, or actually one specific, I think it was William Morris, I can't remember the exact name of it, but a cigarette company was put on trial because this person had smoked most of their life and they developed lung cancer, and they decided to perpetuate a lawsuit against the cigarette company. Now, I'll tell you something about the cigarette company in a moment and what they did, but the result of which the cigarette companies had to put those warning labels on the side of packs of cigarettes. What ended up happening was the cigarette companies, their lawyers, argued that, statistically speaking, just because there's a correlation between two variables, meaning people who smoke versus whether or not they developed cancer, just because there's a correlation does not mean that one caused the other. The correlation, there could be correlation between any number of random variables. But mathematically speaking, statistically speaking, you cannot prove it. Now, how does that relate to what we're doing today? The way we prove causation is through well-designed experiments and observational studies. Surveys, unfortunately, don't prove the cause. Surveys are very helpful, but they don't prove the cause because obviously people can lie on a survey and they don't have to be truthful, and that information, if you're trying to prove cause, not very helpful. Now, the interesting thing is that no one had ever really done an observational study. Okay, here is person A, and they take up smoking at age 15. Let's follow them throughout the next 15, 20 years and see if they develop cancer. I'm sorry, no one had done that in the 1960s. No one had done that. I mean, it's very clear to us today that smoking causes cancer, but they could not say that it caused until they actually did the proper observational study. Unfortunately, you can't do an experiment because that would be unethical. You can't just be like, okay, 15-year-olds, start smoking and smoke for the next 15, 20 years, and then we'll measure if you've developed, lung cancer or not. You can't force someone to participate in that experiment. Unethical. But you can do an observational study. Eventually, yes, were able to scientifically prove that smoking causes cancer through a proper observational study, but it took time. No one had done it in the 1960s. Now they have. Okay. One last main point to make. I have a couple sample problems that I want to do at the end, but one last point to make. Let's talk about this. Let's talk about bias. Questions or procedures, if you're talking about an experiment, within a survey or experiment can introduce bias and affect the results. One way we try to avoid bias is by random sampling. But another way to avoid bias or to reduce bias is with the proper questioning or procedures within a survey or experiment. What you want to do is you want to avoid poorly written questions and procedures. I have my notes right there. For example, you don't want them to be confusing or wordy. You don't want them to encourage a certain response. And I have examples of that in a moment that I'm going to show you. You don't want them to cause a certain reaction. And you don't want them to address more than one issue. I should specify this over here. We do not want. There we go. We don't want them to be confusing or too wordy. We don't want them to encourage a certain response. We don't want them to cause a certain reaction. We don't want them to address more than one issue. This is how we can reduce bias. Now, unfortunately, there is some bias that we can't just get rid of completely. We cannot completely get rid of bias whatsoever. What do you mean budget Khan Academy? Do you have to pay money for Khan Academy or some junk like that? Also, I'm live interacting with you for those who actually do show up live. Anyway. Exactly. And I play video games maybe sometimes. Oh, goodness gracious. Okay. Let me bring up the examples that I want to show you. Okay, so for example, I do have my textbook here, which I need to bring up in front of the camera. And I'm going to zoom in a little bit. Talk about some questions, and I'm going to talk about a real-life example before I wrap up here today. Ah, come on. Almost there. There we go. Good. Anyway, determine whether each question is biased or unbiased. If biased, explain your reasoning. Numbers 18 through 21. Number 18. Do you think that the school needs a new gym and football field? Well, this is a biased question. It's addressing more than one issue. You may have a certain opinion on the gym, and you may have a separate opinion on the football field. But if they just ask it together within the same question, it is biased. It's conflating one with the other. Number 19. Which is your favorite football team? The Dallas Cowboys or the Pittsburgh Steelers? This question is biased as well. Not only is it addressing more than one issue, the Cowboys or the Steelers, but it's encouraging a certain response. You may hate both of them. You may be like, no, thank you. The vast majority of people who are surveyed with this question may say, no, absolutely not, nothing, neither of them. It's biased. Number 20. Do you play any extracurricular sports? It's either yes or no. There's no bells or whistles. Number 20, seemingly, is unbiased. Unbiased. When you're trying to design questions, you're trying to design them in a certain way where you are cold and calculated and you bring none of your own emotion or personal biases into the question itself. Number 21. Don't you agree that students should carpool to school? That is biased. It is encouraging a certain response. Again, with these types of questions, you want to try and avoid bias by any means necessary. There are ways that you can do it. One way, of course, is with questions within a survey. Now, let me show you something here. This is a real-life story. Look at this. In 1936, there was this magazine in which they reported the results of a statistical study used to predict whether Alf Landon or Franklin Delano Roosevelt would win the presidency. The sample consisted of 2.4 million Americans registering, they say including subscribers, registered automobiles, telephone users. Basically, they put out the word to in their magazine, hey, respond to this survey. 57% said Alf Landon. They wanted Alf Landon to win the presidency. They said, Alf Landon's our man. Alf Landon's the guy that we got to do it with. 1936. You've never heard of President Alf Landon. In fact, this is the electoral map in 1936. And you can clearly see what happened. Roosevelt won in an overwhelming landslide. And you can see the popular vote ended up being Roosevelt was 61% of the popular vote. Now, I'm not going to really focus on these questions. I'm going to focus on why. Part of the reason why this ended up being such a huge disparity. Oh, the poll is 57% Landon, but then in reality, only 37% voted for him because it was a biased survey, completely biased. They mainly asked people who read their magazine. And the people who read their magazine were people that had a certain political ideology. And if they had that certain political ideology, most of them pretty much wrote in, oh yeah, Alf Landon, he's our guy, even though he's probably really unpopular in the grand scheme of things. It's very biased. It's not random. This is called voluntary response bias. That's not so much important. But the fact that they were only surveying people who shared their political ideology, that completely skewed their results. That's a real life thing. Stuff like that happens in real life. If you're ever talking about an online survey, like if you've ever seen those like silly online surveys like, oh, who thinks that we should impeach the president, or whatever you want to say to that effect, it's a completely biased result. Online surveys are completely garbage. If you want a better survey result, there's actually a website that you can go to if you want, I'm talking mainly political polls, but if you in terms of politics, there's something called realclearpolitics.com. If you go to that website and then you click on polls, which is one of the tabs that pop down. I'm actually going there right now. Realclearpolitics.com. And then, under the banner to the far left, there's the word polls. If you click the word polls, it'll show you the most recent polls that were done. Now, these are just individual polls. what Real Clear Politics does is it takes what they call the Real Clear Politics average of these polls, but that's not the point, though. The point being that these are actual legitimate polls. These are actual legitimate polls, not some stupid online poll on some guy's website that people are going to be like, oh, look at that, 100 out of 100 people say, impeach him again. It's like, no, that doesn't represent the population of the United States. It just represents the people who answered your survey. So it's one of those things. Now, what we're going to do with this data is one thing. That's for another lesson. Let me just show you very quickly. I'll try to zoom in on this. Here we go. Some sample questions from a practice worksheet. Oh, Joe. Mark, you getting heated. Here's the thing. I am incredibly passionate about statistics, and I am incredibly passionate about people being unbiased in the information that they present. If people are presenting information as fact when in reality it's just their own opinion, and they present that opinion as fact and then denounce everyone who doesn't agree with their opinion, again with no facts to back it up, that irks me to the nth degree. I don't care what political party you belong to. I don't care if you're a leftist. I don't care if you're a rightist. I don't care who you are. If you if you denounce people who just don't share your political beliefs or political opinions without facts, without actually having a conversation, sorry, I can't do that. I can't. Anyway, talk about a few of these questions, and I'll wrap up with this today. Numbers 1 and 2 determine whether each situation calls for a survey, experiment, or observational study. Explain your reasoning. Number 1, you want to compare the health of students who walk to school to the health of students who ride the bus. Now, logically, if you walk to school regularly, you're not going to change your behavior. If you ride to school, typically you're not going to change your behavior from here to there, but you could potentially do some kind of survey. Observational study is a little bit more difficult. You want to get the information on the health of the student, and if you do get information on the health of the student, you can't just do it just by watching them, and you can't really just get their medical records. So you're gonna have to survey them. You don't have to do an experiment because you're not going to manipulate anything. You're not going to change their behaviors. You're just going to get information on their health. Number 2, you want to find out if people who eat a candy bar immediately before a math test get higher scores than people who do not. Now, this is a good idea for an experiment. The treatment, the two groups, you have an experimental group who get the treatment of the candy bar and the control group who don't get the treatment of the candy bar. And then they go ahead and take a math test. Now, obviously, if you're a part of the control group and you're not getting the candy bar, maybe you're just upset that you didn't get a candy bar, which is probably why you need to not know that that treatment happened for the other group. It's one of those things where they have to be blinded to that fact, but that would be a good idea for an experiment. There's a treatment, there's a control group, good to go. 3 through 6? Let's just do it. Determine whether each survey question is biased or unbiased. If biased, explain your reasoning. Okay. Number 3, what's your current age? Clearly an unbiased question. Like, come on. Anyway, number 4, do you think teachers should be required to attend all home and away football games? Now, this is definitely a biased question. There's a couple different ways that you can go about it being a biased question. Most importantly, you're asking more than one thing. Home and away football games would be more than one issue that you're addressing. So you don't really want to do that. Do you agree? Oh, which question, Joe? Number four? We'll see. And number five, though. Do you agree or disagree with the following statement? Teachers should not be required to not supervise students during lunch. Number five is a biased question. The reason why number five is a biased question, it is confusing. Yes, Joe, I do agree. It is actually number four was a silly question. Um, Teachers obviously shouldn't be required, but I mean, we do anyway. I mean, we still go to them, or some do who can. There are some teachers who, they have families and they have things going on and they live too far away, but whatever. Anyway, number five is biased. It's confusing to read in the first place. Number six, most teenagers text message during class. Are you one of them? Sorry, just. Oh my gosh. Number six is definitely biased. Not like, ooh, this. Yeah, I know. I agree. Silly question. Yeah, but number six is biased. Are you one of them? Um, I mean, this is like a combination of encouraging a certain response because they'd be like, no, no, of course not, no, or it's causing a certain reaction because um, they feel like they're gonna get caught in something. I don't know. Most teenagers text during class. Are you one of them? Or it's like they even lessen the blow, where it's like, hey, everybody does it. Everybody text messages during class. Do you? Like it's biased on a few different levels. It really is. Let's just read number seven, and I'll wrap up with this today. It's not exactly the same as before, but a research group wants to conduct an experiment to test the claim that students who use laptops in class have higher standardized test scores. State the objective of the experiment, suggest a population, determine the experimental control groups, and describe a sample procedure. Now, not to get into too many details, but the objective of the experiment would be to compare students who use laptops to those who don't use laptops, compare their standardized test scores to see if one has a higher average score than the other. Now, there's a whole bunch of statistical analysis that can happen after the fact, but that's not a point. The point. The population could be, I mean, depending on how big or how small you want to get it, it could just be the population of your high school. If you wanted it to be the population of the United States, that would be much more wide scale, and you would have to survey people in, randomly throughout the United States. It'd be much easier just to actually do an experiment at one particular high school, but that's besides the point. Determine the experimental and control groups. Well, the experimental group would be ones who would exclusively use laptops in class, and those who don't. So you would have to set up a scenario where one group uses them and the other group does not, and there's no crossover. Now, keep in mind, in order to introduce randomness into this, maybe you have like a group of 50 students who volunteer, and you randomly split them 25 and 25. That's where randomness can come into play, and the randomness would also reduce bias. Then describing a sample procedure. Oh, well, I just explained that. Good for me. Yeah. I mean, you could randomly select people within the school, but then they would have to agree to participate in said experiment. It's easier to get volunteers and then randomly split them after the fact. But I mean, if you could randomly select students, that would be even better. The thing about statistics, and I'll wrap up with this. The thing about statistics is that it is more of a science than it is a math. And when you are dealing with more of a science, there's a lot of room for fluffy language and a lot of room for wiggle room or wiggliness, whatever you want to call it. There's always more than one answer when it comes to describing something verbally. And then when you come to a conclusion on something, usually you have to use like the softest of language. Like you're not actually proven something. You've not actually shown something. You've just here's evidence to suggest this particular result that I came to. Confident statements, limited information. This was just the first lesson on this brand new chapter for Algebra 2. If you guys have questions moving forward, please by all means ask me. There will be some follow-up and some assignments within the next couple of days, and we'll deal with it when the time comes. In the meantime, I know Joe's watching. Live stream video game. I've been meaning to do that, Joe. We'll see about, maybe we'll see about tonight. I don't know. If I do, obviously, keep those notifications up. And, we'll see what happens. Anyway, goodbye, all.